Okay, so hi everyone, welcome to today's SciML webinar. Today we're excited to have Ji Qi giving a talk and Professor Daniel Schwab-Koda as our session chair. So Daniel Schwab-Koda is an incoming assistant professor of material science and engineering at UCLA. Prior to UCLA, he obtained his PhD from MIT and worked as a Lawrence Fellow at Lawrence Livermore National Laboratory. His research interests include the development of robust machine learning methods for material simulation and scalable for computing for modeling energy materials. With that, I'll hand it over to you, Daniel.
Thank you very much, Keith. It's a pleasure to be here to chair the session. It's my pleasure to introduce today's speaker, who's Ji Qi. Ji is a 50-year PhD student, material science and engineering at UCSD, and works with Professor Xu Pingyao. Ji earned a bachelor's in engineering physics and was awarded a couple of awards, including the Outstanding Student Award by the Department of Applied Physics at Hong Kong Polytechnic University in 2019. And more recently, he was also granted a dissertation year fellowship with material science and engineering program at UCSD. So Ji has extensive experience with machine learning, especially for material science, especially in the areas of fitting and enhancing machine learning interatomic potentials, for example, to investigate lithium diffusion in solid electrolyte materials. And today, Ji is going to present his recent work on training structure sampling and with a talk named Dimensionality-Reduced Encoded Clusters with STRATIFIed or direct sampling for robust training of MLIPs. So Ji, the floor is yours. Thank you very much for the talk.
Yep, thanks, Professor, for the great introduction. And today is my great pleasure to present my work at the SCML webinar at MICDE UMich. So I would like to introduce the direct sampling for robust training of machine learning intermittent potentials, which is a very recent work done by our group. And for the presentation today, here is the overview. I will start with brief introduction of the background information of machine learning intermittent potentials and extrapolation issue for MLIPs. Also briefly introduce what is the universal M3G-net potential. And in the main topic, I will discuss about direct sampling work and show you two cases that we use the direct sampling to train robust machine learning intermittent potentials. And at the last session, I'll give some tutorials for the usage of direct sampling to train MLIPs for different systems of interest. So let me start with the introduction. So here I give you an animation of the water molecules at 300 Kelvin. The motion of the water molecule is derived from the Newton's law of motion, where the interaction between the water molecules are actually defined on the potential energy surface. And traditionally, there are two ways to define the potential energy surface. The first one is used in the classical molecular dynamics, where we use rigid functional forms, like the example here, to define the potential energy surface. And with these rigid functional forms, the scalability of the classical molecular dynamics is very well. It can be used to millions of atoms for microsecond scale simulations. However, its accuracy is it's relatively poor, and the transferability is also not very well because we always need to invent new functional forms for different physical interactions. Well, for the second way to define the potential energy surface, we try to solve the Schrödinger equation with some methods like density functional theory or DFT to get the potential energy information. And with this method, the ab initio molecular dynamics can be highly transferable and accurate to the whole periodic table. But because of the poor scaling, it's only applicable to, say, hundreds of atoms for below nanosecond scale simulations. And here comes the machine learning intermittent potentials, or MLIPs. So there are two major enabling components for MLIPs. The first is the local environment descriptors that transfer the structural information surrounding each atom to local environment fingerprint. And the second component is a machine learning algorithm that connects those local environment fingerprints to the potential energy surface information as ground truth, which is the training structure and training data from training energy and forces from ab initio simulations. So this way to define the potential energy surface by the MLIPs has been verified to have a combined accuracy of AMD and efficiency of classical potentials for a lot of different systems. And this framework has become a game changer for the material simulation in many aspects. However, we also know that the MLIP suffers from poor reliability for extrapolation. Here I show you a schematic diagram showing this idea that the extrapolation is defined as prediction by MLIPs that's for structures that are out of the training domain. So for that kind of structures that is unseen during the training process, the MLIP can have very wrong errors and very large errors. And in order to have reliable simulations, we have to include those target scenarios of simulation into our training structures. So on the right, I give you a real case example to talk about the extrapolation of MLIPs. So in this example, the Gaussian approximation potential, we train the Gaussian approximation potential with 3 training sets, and the relative location of the training structures to a target simulation structure, which is the polymorph of silicon, is shown in these first 3 diagrams. You can see that the red dots represent the polymorph feature, while the green dots represent the training set. Okay, so when we have when the training set doesn't have the polymorph structure, we have a relatively large error compared with DFT with respect to the energy of the polymorph structure to the ground state structure of silicon. Well, if we have if we augment the training set with some closed structures that are close to the polymorph feature in the feature space, which is the closed model in the figure B, then we have improved accuracy for the prediction of the energy difference between polymorph structure and the ground state structure. Well, in the third case, where we exactly include the polymorph feature into the training set, then the gap model have the best accuracy over the 3 comparison cases. So this case shows us the importance of our training structure to cover a diverse feature space, especially those that are interested in our target simulation scenario. So in this presentation and in our work, this is actually the aim or the motivation of our work to sample a training structure set that's cover a diverse feature space so that we can have reliable machine learning potentials. And I would like to first introduce the use case for the first scenario, which is on our M3GNet inertial potentials. So this M3GNet potential is developed by Dr. Chi Chen and Dr. Shuiping Ong in our group at UC San Diego. So in this model, we use graph featureizers and perform many body computations to incorporate atom and bond information as well as bond angle information into our local element features, and then go through 3 layers of graph convolution to extract and update the bond and atom features sequentially. And in the final gated MLIP layer, we concatenate and process the atom features to predict the atomic energy and sum up those atomic energy to get the potential energy of each structure. So this M3GNet inertial potential has been trained on over 180,000 structures that are obtained from the DFT relaxation trajectories in the material project. So this model have been verified to perform a lot of different simulations for that need the information from potential energy surface. For example, here the structural relaxation has been done for 3,000 test structures in the material project, and you can see that when we calculate the potential energy of DFT relax structures, over 50% of the test structure we tested have a small error of 14 MeV per atom, while for the structures, if we relax it with MCGNet, then we have a very close error of 15 MeV per atom. So it demonstrates the ability of MCGNet to perform a structure relaxation for those test structures that are in the materials project. However, even MCGNet suffers from the poor reliability for extrapolation. So here you can see that I'm showing you two test sets. The first is structural relaxation for sodium-containing materials in the material project. Okay, while the second test set is 800 hypothetical sodium-containing materials that's extracted from metaverse.ai, which is a database consisting of 30 million hypothetical materials by isovalent substitutions of structural prototypes in the SSD database. Okay, so this test set is out of the training domain because they are definitely not included in the material project. Okay, and you can see that although they are all sodium-containing materials, for this hypothetical material test set, we have much larger test errors in terms of the predicted energy above Hall compared to DFT. Okay, and the test error it's a few times higher than the error for sodium-containing materials in the material project. Okay, so we see there is a very large space for improvement for the extrapolation of MCGNet, and we want to solve this by a data perspective, which is to improve the diversity of the training set. And before that, let's have a look at what is exactly included in the training set of MCGNet. So the MCGNet training set is actually constructed with this manual sampling method, or we say a domain expertise method that we select the first, middle, and last relaxation snapshots from the materials in the material project relaxation trajectory. So in total, there are around 186,000 structures. Okay, so with this method, you can imagine that we already try to sample as diverse as possible the relaxation trajectories and get the features from the relaxation trajectories. But if we look at the energy, force, and stress distribution of this manual sampling set with all the material project relaxation structures, we can see that in those relative uncommon regions, there are definitely energy and forces that are missing or not sampled in those relative uncommon ranges. And on the left, I'm also showing you a PCA feature space, just visualizing the first two principal components of the feature space of MCGNet formation energy model. You can see that the manual sampling set definitely covers the common features, but for uncommon features that are on the boundary of this feature space, it's not really covered in our training set. So we see a potential that if we can better sample the structures in the material project realization trajectory, then we have a chance to get a more robust training set and a more reliable MCGNet model. So to solve this, to try to achieve this goal, we come up with this direct sampling workflow, okay, which is to actually, in one sentence, to do a stratified sampling in the feature space. Okay, so what exactly we did is that we use MCGNet formation energy model to featureize the structures into the feature space and perform PCA to reduce the dimensionality of those features. And then we do clustering for the structures in the feature space according to their location in the feature space. So the clustering can be illustrated in this two schematic diagram where we have example diagram, where we have 50,000 snapshots structure from AMD. And if we do clustering, then we will we can set 3,000 clusters that you can see some of the clusters have a large number of structures in the common region, while there are also clusters in the relative uncommon region. So with this clustering, then we do a final step of stratifying sampling in a way that we select the fixed number of sample from each cluster. So in this scheme, we can select both common and uncommon features from those clusters. Okay. So we applied this direct sampling workflow to the multiple project realization trajectory structures. And to have a fair comparison with the manual sampling effort, we select a very similar, we did a very similar amount from the realization trajectory, which is around 186,000 structures. And you can see that just by visualizing the first two principal components, we successfully sampled also the the relative uncommon regions of the features in the feature space. And we also use the feature coverage score, which is defined by the evaluation of for each feature, for each principal component, we can divide the range of distribution of the feature in the mature project by different bins. And if the subset of the structure sampled each bin, the C sampled equals to 1, while if it's not sampled, then it's equal to 0. So with features coverage score equal to 1, it means that all the features are sampled. While with a smaller feature coverage score, it means that there are some missing features. So we can see by the feature coverage score for all the first 14 principal components, the direct sampling set has a very large feature score of close to 1, while the manual sample set has a much smaller feature coverage score. And more importantly, we can see how this clustering and stratified sampling in the feature space perform for the properties related to the potential energy surface, which are energy, force, and stress in the material project realization trajectory dataset. You can see that the orange colors bars, which represent the direct sampling data, has a very comprehensive coverage for those relative uncommon energy, force, and stress values, so that we have a data set with larger mean absolute deviation than the manual sample set and then the MAD of the realization trajectory data set in material project. So with this better coverage of common and uncommon features and properties, we use the direct sampling data set as the training set and train MCGNet, and also compare with the MCGNet trained with the manual sample data set. So we have one architecture, MCGNet, and also two training set as we discussed. And for the test set, we also have two. That's around 5% of each of the direct sampling and manual sampling test set. While we exclude those overlap structure that are already used in the training set of each model. So you can see that on the above three figures, I show you the correlation of energy, force, and stress predicted by the MCGNet direct model with the energy, force, and stress by the DFT. Okay, we can see that for the two test set, the MCGNet direct model has a relative comparable accuracy in terms of the R2 score and MAE values. Well, if we look at the lower three figures, which is the correlation plot for MCGNet manual sampling model, we can see that for the direct test set, it has a much higher error compared to the manual test set. Okay, so this shows us that the MCGNet trained with direct test sets can have more consistent accuracy for more broad structure space, while the manual test set it's more or less only reliable for the relative common structures, while it has larger error for the uncommon structure that it didn't sample in the training structure. So with this MCGNet direct, we further did some tests on the simulation reliability for extrapolation. So remember that we showed this test set for hypothetical sodium-containing materials in the first few slides, and now we perform the test with the MCGNet direct. you can see clearly there's an improvement in the error for the predicted energy above Hall compared with DFT. Also, we have two more test sets for oxygen containing hypothetical materials and sulfur containing hypothetical materials. So for oxygen, we don't see a very obvious improvement, which can be majorly attributed to the fact that in the MP material project, oxide already extensively sampled by the manual sampling method, while for sulfur containing material, which allow less frequently showing up in the material project dataset, we can still see a obvious improvement. So this concludes the first case, and we also applied the direct sampling work to some specific material systems that are not like the universal dataset that we show in the first example. Well, for this second example, I want to show you how people usually train structures for this kind of for specific material system. So we already discussed that MLIP is not reliable for extrapolation, so which necessitates that we have to do some iterative augmentation of training set. And very traditionally, what people do is to use DFT to calculate some test structures, and then we use MLIP to predict those test structures and evaluate the test error. If we have a large test error for those test structures, then we can augment those test structures into our training set. So this manual evaluation with DFT can be very slow. You can imagine that. So there is a significant improvement when we have the active learning workflow. Here I show you the schematic diagram as an example for which is gotten from the active learning workflow by moment tensor potential. So what they do is that they invent extrapolation grid that can evaluate if the MLIP it's doing an extrapolation of structure, or it's actually predicting a structure that's very similar to existing training structures. If there is an extrapolation attempt, then they will add those these structures into the training set. So in this method, you can imagine that we don't need DFT to do the evaluation of extrapolation, so that we can evaluate much larger structure set and get a more robust training set with smaller cost. However, even with this well-defined active learning workflow, it still requires iterative optimization of the training set as well as the training as well as the MLIP. Okay, because we need to do DFT calculation for those new structures emerging in the active learning workflow. So this can be time-consuming for especially for systems that we have more complex chemistry or larger number of different elements. So we want to eliminate. Yeah.
1 second. Let me just stop you for a second, just to clarify one question from the audience is regarding the mapping from the representation to the PCA. So what features do you use to make your PCA analysis before?
You mean okay. So here, let me go to the page. Yeah, so the features that we process with the principal component analysis is actually the features we obtain from the MSGNet formation energy model, which is actually the we take out the intermediate output from the final graph convolution layer as the features for those structures. And those structures those features have the fixed dimension of 128 elements. We actually did some comparison for different encoders, like the MSGNet formation energy model or the magnet formation energy model. And we found that the MSGNet formation energy model can have improved explained variance. The features from the MSGNet formation energy model can obtain better description for those structures in the multiple relaxation trajectories. So that's why we are using it as the featureizer. Yeah.
And in that case, you're also using in a per environment basis, or you pull it over the structure, the whole structure?
Yeah, it's a per structure feature.
Okay, thank you.
Thank you. Let's go on. Yep. So in this, let me continue to discuss about the our application of our direct sampling workflow to try to eliminate the need to iteratively augment the training set. Okay, so especially in this case, we are trying to get a diverse training set for the titanium hydrogen system, which is a challenging system for molecular dynamics because the hydrogen is diffusing very fast in the titanium. Okay, so we have 3 data sets here. The first set is obtained from MCGNet molecular dynamics. So we perform MD-NPT for 274 MD scenarios and obtained 274,000 trajectory structures. So those MD scenarios compose of a range of compositions for titanium hydrogen compounds, and which are obtained from consisting of 5 different lattice systems, also different at 3 different temperature from 300, 1000 to 3000 Kelvin. And we also include green boundary and bulk structure in this structure set. And for the test, for the other set, which is obtained from MTP active learning, we perform the active learning on the exact MD conditions as the 274 MD scenarios in the first case. Okay, and we obtained 2063 structures from this MTP active learning scenario. And while in the last data set, we perform AMD for 3 titanium hydrogen bulk structures spanning HCP, BCC, and FCC lattice systems, and we obtained 75,000 MD snapshots at 1000 Kelvin. So by looking at the feature space, by looking at the PCA feature space, we can immediately see that the MCGNet MD structures can actually mostly cover the features sampled by MTP active learning and AMD. Well, especially for AMD, I mean, both the MTP active learning and MCGNet MD structures can cover their features. Well, for the active learning and MTP active learning, there are some features not sampled by the MCGNet MD. But most of the regions, I would say, is well covered by the MCGNet MD structures. So as a proof of concept, we again compare the direct sampling with manual sampling for the MCGNet MD structures. So we did 2 steps to downsize the MCGNet MD structures. The first step is to sample on each trajectory, because in each trajectory we have 20,000 relaxation. MD trajectory structures, and we just select 1,000 from them with the direct sampling. And by visualizing the PCA feature space, we can see that the direct sampled 1,000 structure covers not only the most common region, but also the regions in the feature space that are not relatively rare in the feature space. While for the manual sample method, which we use a fixed interval of 10 femtoseconds to select the structures from the MD trajectory. In this case, you can see that in those feature space that are relatively dynamic, the trajectories are not well sampled. There are larger gaps compared to the direct sampled subset. And then as the second step, we apply the direct sampling for the whole 274,000 structures. Again, we will achieve a more comprehensive coverage in terms of the 2D PC feature space. So yeah, this is just a proof concept that direct sampling also can give a more comprehensive coverage than manual sampling for this kind of specific system. And with the direct sample data set, we actually, as we showed in last slide, we select around 1,000 structures, and we train MTP with two training sets. One is the 1,000 direct sampling structures, and the other is the 2,000 active learning structures. So we have one consistent test set, which is 300 AMD structures. And we use the exactly same DFT settings to do this training and to generate the training structure and test structures. So we can see that briefly what we got is that the MTP direct gives comparable test energy and force errors for those structures of AMD compared to the MTP active learning model. And we further continue to do more tests between the active learning MTP and the MTP direct. Sorry, excuse me. So here what we did is the MD simulation at a range of temperature to study hydrogen diffusion in titanium hydrogen bulk structures. So there are three different structures in MD simulations: FCC titanium hydrogen and BCC titanium hydrogen, also HCP titanium hydrogen. And we see that in those cases, we have a consistent trend that from the two MTP models, the hydrogen diffusion have the largest diffusivity in the BCC titanium, while it has the lowest diffusivity in the FCC titanium. And this trend agrees very well with the experiment, and also the simulated diffusivity and activation energies also match with experiment. And we also compare with the mean square displacement of hydrogen diffusion by ab initio molecular dynamics at 1,000 Kelvin. You can see that just briefly, the two MTPs both match with the AMD simulation results. So beside the ambient temperature simulations, we also did some further tests for the reliability of our MTP direct model. So in this case, we applied the MTP direct as a pre-trained model and pass it through to the exact active learning workflow that we applied to train the active learning MTP from on the fly. Okay, you can see that. Let's first look at the dashed lines, which is case one, training from scratch, which is training from 92 initial structures of the molecular dynamics. You can see that we have 91. We have 91 bulk structures in the structure set, and just one gas structure, which is hydrogen gas, in the training set. So, so for the active learning at 300 Kelvin, we have achieved reliable MD runs after within 10 iterations of active learning, which is also the case for 1,000 Kelvin. While for 3,000 Kelvin, it took the active learning from scratch for in total 28 iterations to achieve reliable simulation for all those 91 simulation cases. While if we start from the direct sampling dataset as the pre-trained model and pre-training dataset, then we can see a significant decrease in the number of required active learning iterations. To be exact, for those cases in the 300 and 1,000 Kelvin, for the 91 crystalline structures of titanium hydrogen compound, we can see that without any active learning iterations, we can already complete all those simulations at 300 and 1,000 Kelvin. While for 3,000 Kelvin, we still need a few active learning iterations to better sample those structures, but it achieves the reliable simulation after just 5 iterations of active learning. So this shows us that the MTP, the direct sampling can provide a more robust initial training set that promotes the convergence of MTP active learning. This actually echoes very well with the results published by the MTP developers, that if we do on-the-fly training with some well-designed pre-training dataset and pre-learned MTP, then we can significantly decrease the needed amount of DFT simulation and training iterations compared to learning on the fly starting from scratch. So yeah, here I want to draw a conclusion to my presentation today, that direct sampling is an agnostic approach to generate diverse training structures to MLPs across any compositional complexity. And we demonstrate the direct sampling workflow in two cases. One is that we train a better M3GNet universal potential with improved reliability. And second is that we train a reliable MTP for the titanium hydrogen system without iterative augmentation of training structures. And I think the next session, I will talk about the tutorials. So should we take some questions here or afterwards?
I think we can stop here and ask if there are any questions. Thanks very much for now, G. And the floor is open for questions from the audience.
I can ask a question or two.
For sure, Keith.
All right, yeah. So thanks G for the talk and sort of explaining the direct sampling method. It seems like a really useful way to, when you have a data set, to sample it, I guess, effectively. When I think of sort of the problems with difficulties with training machine learning potentials, there's this issue of, well, how do I know what's outside my data set? Because those are the most difficult things to find, in a sense, because maybe you won't get to that rare polymorph using MD simulation. So how do you think about, I guess, that problem? I think you talked a bit about active learning, but how do you think about sort of extrapolating beyond the direct method, so to speak?
Yeah, so I think that's a great question. So I think in general, for any machine learning intermediate potentials, it's very important to verify that our model is reliable for the simulation of target conditions. So to exactly answer a question, how to I mean, how to know if there are such extrapolation? I mean, my first answer is that we just need to sample from the exact target simulation scenarios. For example, here I'm interested in the diffusion of hydrogen in different titanium lattice systems. Then in the MD trajectory, I did the in the MD simulation, I exactly did the simulation on those target scenarios from the target temperatures. So in this case, I would be more or less confident that those structures that I sampled is already representative for the target simulation scenario. And I think this is also the same logic for MTP active learning. Well, in terms of future aspect, we can also try to define some extrapolation criteria, like what they did for the MTP active learning, to evaluate if there is any other extrapolation behaviors that is attempted during the MD simulation. But I would say in real case, after we verify the machine learning potential, people usually don't recalculate the extrapolation grades, things like that, in the production runs. So the verification step is the most crucial part from my point of view.
Perhaps a follow-up question to that, G, is that during your talk, you mentioned about the reliability of a couple of trajectories and the convergence of your model's ability to extrapolate with a number of active learning iterations. So can we often have a problem defining what's reliable, right? Like, so as Keith mentioned, the keys of finding things which are outside of the training set and saying that this structure should not exist or should never be sampled because it's unreasonable according to the potential, to the actual ground truth potential energy surface. So in those analysis that you did, how did you define this reliability? How did you define that a trajectory is unreliable? And did you compare it to any ground truth potential to do that?
Yeah, so I think in terms of reliability, what I'm talking about is actually how the prediction by the MLIP compare with the training structure or the ground state truth, which is from the initial simulations. So for example, if we have extrapolation, then the energy and force will be very wrong compared with DFT. So yeah, that's how I try to evaluate the reliability. For example, for the titanium hydrogen case, except for besides the energy and forces, we also evaluate the MSD by the two MTP models compared to the AMD simulation. So I think this kind of test can help us verify the reliability. Yeah.
Okay, thank you. We have a couple of questions from the audience here. So there are questions asking how many CPU or GPU hours did you use to create these training data sets?
Thanks for the question. And so for this, let me recall. So firstly, for the M3GNet universal potential model, those structures are actually generated by the DFT relaxation done by Material Project in the last 10 years. So I didn't regenerate those structures, but this is a good question in terms of the time controlling step of this workflow is really to generate those M3GNet features of those 1.3 million structures. So I did a parallel calculation to generate those structures in say like 100 jobs, and it takes, I guess, a few hours for each of the job to calculate the structure features. And in terms of this training set for titanium hydrogen, each case, because the hydrogen, as I already discussed, the hydrogen is highly diffusive, so we use a very small time interval of 0.5 femtoseconds, which is comparable to the step interval used in the AMD simulations. So this 10 picosecond molecular dynamics each takes a few hours to complete. So on one CPU. So in total, I mean, it's like thousands of CPU hours for this generation of the data set. Yeah. But I would say it's definitely hundreds or thousands times smaller than the required CPU hour if we use ab initio molecular dynamics. And in total, I trained this moment tensor potential for the MTP direct in just 1 week. Well, for active learning, it may take longer time. Yeah.
And I assume that one of the goals is to reduce the amount of data that we're sampling, right? So
yes,
and that definitely drastically reduces already the number of evaluations.
That's right.
And another question regarding the architecture is when you say the universal potentials, how you're defining the universality of these potentials in terms of simulating any element of the periodic table?
So this M3GNet model is already readily applicable to simulate 89 elements in the periodic table or any composing compounds by those 89 elements in the periodic table. So in principle, it can be further generated to larger number of elements, but we have this number because this is what the scale of the existing data in the Material Project. So yeah, in terms of universality, I mean that it's applicable for this set of structures. Yeah.
All right. Other questions from the audience relate to the sampling, especially in the PCA space. So, for example, when you're doing the clustering, are you sampling the blank space as well? That's one of the questions from the audience.
So, this is a great question. We are actually only sampling from the existing structures. So not the blind space in the PCA feature space. So we still don't have a very good methods to do this kind of reverse simulation that we know one point in the PCA feature space and reverse to the geometric space to get the structure. So that's why we can only try to sample a diverse feature space by some simulations like molecular dynamics or some manual strings to the structure. But so this workflow majorly, as Case said, it provides a comprehensive coverage for the existing structures and downsize the structure to a size of necessity. But we still cannot sample beyond the structure that's sampled by the configured space sampling in the first step. So in future, I mean, this can be one very interesting direction.
Mm-hmm. Yeah, very interesting indeed. And how do you pick the hyperparameters of the clustering, for example, the number of clusters and number of principal components that you're using, for example, to project your representation?
So yeah, let's first to explain the number of principal components I selected these supporting slides. That in the M3GNet universal potential case, I selected the first 14 principal components of the M3GNet features according to the K-shares criteria, which actually drops any components whose eigenvalue less than 1. So you can imagine that this means that we select the principal components that explains more variance than any single variable. So that's how in this workflow, we choose the number of principal components just according to the K-shares criteria. Okay, and I think we also asked about the how to choose the number of clusters. So I mean, for different work, we'll have different suggestions. Well, it majorly depends on the number of structures you want to sample. For example, here for the moment tensor potential for titanium hydrogen, we sampled around 1,000 structures, where the active learning can actually give us a very good reference number that the active learning MTP sampled 2,000 structures. And for different frameworks, by studying the literature, we will know approximate number of structure we needed for different complexity of the machine learning potential model. For example, for moment tensor potentials that have describing 2 elements, usually around 1,000 atoms is a good number. While for other potentials, it may have it may require a different number of structures. This is actually related to the complexity of the descriptors of the different machine learning intermediate potential frameworks. Yeah.
Sounds great. One related question is, we can also think of this splitting or this clustering not in terms of the representations or the principal or the reduced dimensionality representation, but also in terms of energies, forces, stresses, and so on, right? So we could try to do that clustering in this space. So how did you see any differences by trying that?
Yep. I think this is a very meaningful question, and my answer is that what I did here, you see, I show you the distribution of the different test set. Actually, in this plot, direct sample test set, direct sample set, the manual sample set, and all the MP trajectory set. This is the reason why we can show this is that the DFT simulation I already performed. But when we have the MD trajectory that we still don't have this information, then we cannot do such sampling in this energy, force, and stress space. Also, I don't think just the energy, force, and stress is enough criterion. We will also be interested in things like composition, bond distance, like atom density, things like that. I mean, a lot of different features can be included in those features, and it's especially I think it's especially hard to find the weighting between different properties that we choose to do this kind of clustering. Depends on the properties. But in the feature space of the M3 model, we see it's a very good correlation with those features to the target properties, like the energy, force, and stress, and other properties like bound distance, composition. So I think this is already the optimal feature space that I can obtain for now. Yeah.
All right. Yeah, thank you. We answered a lot of questions from the audience. The space is still open for questions. I can ask an additional question that I have, which is every time you do an IMD simulation, you're sampling such a large amount of configurations, and your down selection method is designed to, for example, decrease the training time of these networks. But do you feel that, on the other hand, we're also wasting that information that we sampled by not including all the data that we have available?
So yeah, this is I mean, also a question I'm thinking about, and we still honestly we still need more verification to see if it is always needed to have as large data set as possible. But from my own understanding, I don't think it's necessary to go to a scale, say millions of structures for training, just because we have the ability to extend to that scale. I mean, this is because I think having overlapped structures in the training set wouldn't help to improve the accuracy a lot. And if we sample a lot of very similar structures, then the training will also be overfitted to the common structures. So I mean, that's my intuition. But I see a lot of recent works that in the deep learning field that we use a lot of training structures, like millions of structures. So I'm also doing some investigation to see if those are necessary. Yeah.
All right, thanks. So this is just to sum up and before we transition to the tutorial, I think it's a really interesting approach to really reduce training time and to find new ways to sample the configuration space in a more efficient way. I think the analysis that you do in terms of robustness and in terms of reliability of potentials is something that the field, the community is very interested, because we want to have this universality of neural networks, but also universality across all possible simulations we could think of. So it's really important to come up with new strategies to do the sampling, to do the analysis of robustness in the most data efficient way possible. So it's a critical thing to really enable larger scale simulations and to enable analysis of dynamic systems, as you presented in the case of titanium hydrides and many others. So it's very exciting to see that, and I look forward to the tutorial as well. So for the audience, we can keep asking questions in the Q&A and interrupt us, and we can try to interrupt more frequently in the tutorial if you have any questions. But we look forward to that.
Thank you, Daniel. Yep. So thanks for the nice conclusion, and I will move on to the tutorial session. So in this section, I mean, so all the codes related to this work has been implemented in the materials machine learning package, that's Python package built by our group, and also the data needed to reproduce the results can be downloaded from Figshare. Let me see. I think I need to reshare the screen. Give me 1 second. So yeah, this is the data set that we use to train the two MLIPs. First is the M3GNet inertial potential, and second is the moment tensor potential for titanium hydrogen system. And we also have some data set released to reproduce the results that I will show in the notebooks. And the link for this Figshare, I mean, I don't think you need this for now for this tutorial, but I will send you in the chat. And you can also find it in our manuscript. So so let's go to the code implementation and notebooks in the memo. Okay, so as I discussed, this memo is a Python package developed in our group to perform simulations related to machine learning simulation and material science. So the notebooks for my direct sampling workflow can be found in the workflow trajectory and the directory and subtrajectory. So I give two example notebooks. The first one, it's about how we generate the the structures from material projects trajectories, and second is about titanium hydrogen material system. So I can go through this step by step, that how we perform our results, get our results from the 1.3 million structures. So as one great question from the audience, actually the time controlling step for this sampling workflow is the step where we process the MCGNet features by the MCGNet formation energy models. And so this pre-processing step has already been completed, and this can be downloaded in the Figshare link. And in the direct sampling workflow, we can, okay, actually, let me go to the code where I define this workflow. So the sampling workflow is defined in this sampling subpackage in the memo, and it's actually defined as a pipeline of sklearn, and it's just simply composed of these 5 steps. First, structure encoder to encode the structures. So you, you can feel free to change to different structure encoders from MCGNet structure encoder to like magnetic structure encoder, or any structure encoder that you can try to think of. And standard scalar, just the standard, the default version from sklearn that we pre-process the data before principal component analysis. And after the principal component analysis, we do the clustering and select the K structures from each cluster. So, we define this in a way that users can select can customize the different clustering methods like k-means or birch clustering or any other clustering methods. Also, which should be a subset of the pipeline. Subclass of the pipeline class in the sklearn package. And in the select K clustering step, we just do a stratified sampling where we select a fixed number of structure from each clusters. One detailed information to mention about this stratified sampling step is that the way we did it is that the communication between each steps in the pipeline is currently performed by returning some data from after each step. So from the clustering step, we collect the labels and the PCA features as well as the centers, the centroids of each from each clusters from the processed data. And with the the reason why I need to mention is that I want to show you how we pick the structure from each cluster. So if there's we calculate actually that in each cluster what's the distance between the structure features to the label centers. And and after we calculate this distance to center, we rank and select if we if we only select one structure from each cluster, then we'll select the one that have the smallest distance to the center, which will be the most representative for that cluster. Well, if we have multiple features to select, then what we do is that we rank the distance to the center and pick the features with fixed interval. This time is trying to select the representative structures in each cluster. So yeah, so this is how we define the direct sampling workflow with a pipeline from sklearn and 5 steps as we show in the sampling framework. And here with the dataset, you can define this direct sampler, and we don't need to specify we don't need to set the structure encoder because structure is already encoded. We just need to set the number of clusters, the different clustering methods and number of clusters we want, and also how many structures we want to select from each cluster.
A question.
And with the
in the case that we didn't have the pre-processed data, the structure encoder, do we have to also preload the model with the trained weights, or is that something that is already implemented in MAML? The
yes,
preloading of the model?
Yes, we do need to load those, but this loading is already done. If you install MAML, then also we need to install the MCGNet model. Then this structure encoder can directly be applied to process those structures. For example, here I loaded the structures, 20,000 structures from one empty trajectory of titanium hydrogen. Then with the let me see. So yeah, so then with the direct sampling, where we actually don't specify we actually use the default structure encoder, which the MCGNet structure encoder. Then it takes actually 9 minutes to process those 20,000 structures, and yeah, it's ready to use. That we don't need to manually load any features, any weights. Yeah.
Yeah. Thanks.
Yeah. So we need to define the number of clusters that we want to set for the workflow, and usually this is related to one previous question. How many clusters we need to choose? It's definitely depends on the data set we are selecting from, and also the framework of the machine learning potential. Well, I would suggest that we set the number of clusters close to the number of structures we want to select, so that we can have a better resolution for each cluster, and better resolution of the feature space by each cluster, and we can select a small amount of structure from each cluster to avoid overlapping for similar features in the same cluster. Okay, and so with the fit and transform function, that's what people do with the sklearn pipeline. We can transform those MCGNet features, which goes through the standard scalar and PCA analysis, as well as clustering, to a final direct selection result that contains the labeled index that which structures we are selected. So as printed out, we selected 185,000 configurations from the 1.3 million trajectory structures. And as example, we also did some loaded the manual sample structures from the downloaded dataset, and and you can visualize the features as I mentioned, the direct selection, which is the return result from the direct sampler we can visualize how the feature is covered by the selected feature with respect to the all features in the data set, just by simple visualization of it in the 2D space. And we also provided the definition of the feature coverage score, which is defined by, as I mentioned, the different bins in the range of distribution for all the features and how those bins are covered by our subset. So with this calculation, we can get the coverage score for each principal components. So yeah, so as I mentioned, if we already have the pre-processed data set, then the clustering and stratified sampling will take very short time, usually within like 2 minutes. But if we have a smaller test data set, it will be even faster. So yeah, so this is the example for the M3GNet universal potential training set. And you can see, I guess, most of the results can be reproduced from the download data from Figshare by this notebook. And for the titanium hydrogen case, we actually have comparably comprehensive notebook that can reproduce the results that we do in the manuscript. You can see, so we first load the structure for one trajectory, and in this time we do a full workflow that we encode the structure to feature space and do clustering, and then select the structure from the clusters. So by a fit transform method, we can get the selected results, and it actually selected 1,000 configurations according to our assigned number of clusters and number of selection from each cluster. So so as I mentioned, it takes around 10 minutes to process 20K structures. So you can imagine, I mean, it may take a few hours for those 274K structures, but this process can be paralleled to accelerate the processing. And
another question: the processing, when you say that parallelized, is only on CPUs, or do you also offer support for GPU in the processing?
Yes, I think the current implementation, it automatically detects if there is GPU in the resource. Yeah, but yeah, the parallelization can be done in both ways. Yeah.
Okay.
Yeah. So yeah, I mean, it's always good to check the explained variance to see how large the explained variance is for our selected principal components. So in this case, for the titanium hydrogen case, we select the first 8 principal components that has a very high explained variance of around 98%, and which is also shown in this explained variance plot. And we also calculate the we also visualize the feature coverage for this MD trajectory. And in terms of the feature coverage score, we can see again the direct sampling has a better feature coverage than the manual sampling. And lastly, we reproduce the result that how we select 954 structures from this 274,000 MD trajectory snapshots. I mean, those are using exactly the same direct sampler as we used for the M3GNet universal potential. This time we define explicitly we want 954 clusters, and we select one structure from each cluster. Yeah. So yeah, this time, so as printed out, there are 7 principal components selected, and with explained variance of over 98% for those 274,000 structures. And we selected 954 configurations from them. So yeah, again, we visualize the coverage of feature space by the two different subsets, and we can also calculate the coverage score. So, I mean, with these notebooks, I hope that it will be quite straightforward to reproduce our results, and also it will be able to be generated to other material systems of interest. If you have a very large data set, then you can first process the data with our structure encoder and then do the direct sampling workflow to select the subset of any size. And also you can generate your own configuration space by the molecular dynamics with M3GNet models and then do the processing with direct sampling. Yeah, so that's all I want to show for this session. And also I want to acknowledge the funding from Shell. And also I want to say thank you to Lawrence Livermore National Lab, where I actually did internship and generated this idea of direct sampling. Also, we acknowledge the computational resources from SS and NERSC. Thank you.
All right, thank you very much, G, for the great talk and tutorial. Looks like the code and all the features very accessible and ready to use. So that's awesome to see. Do you have any final questions?
Okay.
Out of curiosity, no, I just had out of curiosity, did you see any difference by clustering on the PCA space, the reduced dimensionality versus clustering over all features?
Yep. So I do see some difference, but the difference is not that significant. In terms of we see an improvement when we do the clustering on the PCA feature space, then the coverage of the for the energy, force, and stress will be more comprehensive. But it's I would say slight difference. I mean, in any aspect, these two set will be better than the manual sampling technique. So the PCA is not really a necessary step, I would say. It's just making the workflow even better. Yeah.
Thanks. All right, back to you, Keith.
Yeah. Yeah, so thank you, G, for the great talk and for the thorough tutorial so that we can, I guess people can go ahead and look at your notebooks and learn from them as well. So I'll close off by asking maybe one question to you, Daniel, which is, I guess there's so much work that has been done in terms of sampling data sets and generating data sets. What do you think are the sort of the biggest challenges that people should be looking to solve going forward in addition to sort of the things that she has been talking about?
Yeah, it's a great question. I think there are several approaches and several different levels of challenge. In academia, we tend to focus a lot in trying to reduce the cost because generating training data is pretty expensive, right? Compared to what we see in industrial players that have a different access to computational resources. In academia, we tend to focus a lot on the efficiency of the data and minimizing training costs and so on. So for us, that might be a challenge. That might not be a universal challenge given the disparity of accessibility of computational resources. And those unlock different kinds of questions, right? So if you can go to large-scale data generation, I think that's a super promising approach that allows us to explore what happens in terms of the really big data limit. And if we see new scaling laws that are going to lead to much better models, similarly to what happened in large language models. But on the other hand, on the data efficiency side, which I think is a lot of what G discussed today, we can try to capture more of what are the physics of the systems and what can we learn from all of these models and all of these samples in order to better capture our intuition of the physics of that we're embedding in the machine learning side. So ideally, we would find a compromise between both in which we want to make the least amount of valuations possible in terms of DFT calls, but also the maximum amount of extrapolation without evaluating everything, right? I think one of the big challenges that we have in the field is really assessing this universal reliability criterion. So we can always talk about how widespread is the application of machine learning potentials to a lot of different systems. In the advances that many have been doing, including G's group at UCSD, have focused on opening these opportunities for the whole periodic table and for a whole set of configurations of crystal structures. That's a step forward in really using machine learning as a universal oracle for atomistic simulations. But I don't think we crossed that threshold yet of forgetting about DFT and just using machine learning. We always keep going back to DFT to retrain and to reevaluate and to be pretty confident about that. And so in my perspective, going towards that limit in which we don't have to rely on DFT anymore and we can always bootstrap from machine learning, that's something that we haven't done yet. And perhaps we should be moving forward.
Okay, thank you so much for that perspective.
Yeah, that's a challenging field.
It's very challenging. It's really challenging for sure. So
yeah.
It's great to see so much work and energy in that space.
Yeah. Okay, I think that's all we have for today. Thank you so much for everyone for attending. Just as a heads up, so next week we have Bowen Deng from UC Berkeley talking about ChargeNet, which is a pre-trained universal atomic interatomic a pre-trained universal interatomic potential to study electron-coupled ionic systems. So it's fairly related to what we had today. So thank you, everyone, and hopefully see you next week.
Thank you.
Thanks.